It is now time to talk about those pesky solids. Now, why would we be talking about wastewater solids in the first place? It seems like it's the kind of problem you can't escape. And partially, that's true. Solids have been a problem in wastewater for as long as there has been municipal wastewater collection. It's always been an issue. It's something that, going back as far as you can in history, has always been a consideration we've had to put through our minds and put through our engineering designs and figure out what to do about once we're out in the field. Now, just because the problem, though, has been around forever, doesn't mean it's been at the same level of severity forever. So if you've been imagining that the problem has been getting worse in recent years, you're probably right. Let's take, for example, this example comes from Charleston Water out in the Carolinas. They talked recently about an issue that they had with a major clog that they had encountered in their wastewater collection system. Their number here is pretty incredible. They talk about a 12-foot-long debris mass that they had to remove from one of their wastewater systems. Imagine that, a 12-foot-long pile or mass of debris. And part of this problem was caused by people flushing things like wipes going down pipes. Now, this problem took them 4 days to get out back into operations after they had removed all those. They talk here about having to send a diver down 80 feet in order to remove this clog from their system. They had to bypass 900 feet worth of sewer collection system just to get around this clog that had developed and that they had to get out. This is not the only example. There are plenty of these examples that have been happening in our real world. And why is it? Is this something that's really an accelerating problem? Well, actually, yes. What's changed about all this? What's new that's causing this bigger problem than we've ever had before? Well, it comes from a couple of things. Number one, a good thing, we're getting more efficient about our use of water. There are simply lower flows coming from domestic users and commercial users because people have become more efficient. We're using things like high-efficiency toilet systems. See this nice little green handle? You go up for liquid waste and down for solid waste. This is a higher efficiency way of dealing with wastewater. If you put less into the system, well, then that seems to be more efficient. It just causes problems potentially downstream. And this effect is pretty significant. Believe it or not, domestic water use in the United States, in a lot of places, has gone down by quite a bit. The state of Iowa now uses an average of 75 gallons or less per day per person. That is substantially less than the 100 gallons per day that we're used to thinking about as sort of a baseline threshold. That rule of thumb has changed. And that rule of thumb has changed because people are using things like high-efficiency toilets, high-efficiency shower heads, high-efficiency dishwashers. An ordinary dishwasher these days might only use 4 or 5 gallons to do an entire load of dishes. High-efficiency washers. All of these different things reduce the amount of demand from the domestic side for water coming in, which means less going out, less liquid going out. But that doesn't tell the whole story. Additionally, of course, we have lower flows from things like separation, sewer separation, so that we don't have combined solids coming in from stormwater as well as sanitary waste. Separating those sewers out reduces the amount of flow coming in. And if you're doing a better job of things like I&I control, you may have less flow that is just plain water diluting everything else that goes through the system. And as we all know from the old saw, dilution is the solution to pollution. But if there is less dilution, that changes what you're going to see. And if you have lower flows from things like sump pump disconnects, if you're getting people off of those systems so that they're not charging your system full of sump pump water, which is again going to be just plain, mostly clear water, that's going to change the level of flow coming through. The flip side to this, or the other part of this equation, is that we have higher impact solids coming through, especially wipes. Now, these things are a nightmare. They're going to continue being a nightmare. And you know why they're going to continue being a nightmare? Because wastewater collection systems do not have the same marketing budget as, say, Target. And because you can go into Target and see a sign that says flushable wipes, your ordinary user is going to look at that and think, well, I can flush that wipe. No matter how many signs you put on the side of the bag, no matter how many indications that are put out there, people are going to see flushable wipes and think, well, that must be flushable. You can't get around this kind of over and over branding that's getting pounded into people's heads. If it becomes something that is just conventional wisdom that a wipe is flushable, this is going to be something that's going to be almost impossible for us to overcome. It doesn't mean we shouldn't try. Wastewater systems have a big job to do in communicating to the public that wipes aren't flushable. But again, unless you have a marketing budget that rivals that of Target or Walmart or any other place, it's going to be very difficult to overcome the argument that wipes must be flushable because that's what the sign said in the store when I bought it. Now that's a big problem, and so also is the rise and the increase of FO and G. And of course, when we have fats, oils, and greases, when we have just age and neglect, when we have things collecting in our systems, kind of nasty things, and as they build up, as they accumulate, and as they become larger and larger masses, well, so become the problems that we encounter. So you put these things all together and you have sort of an equation. I'm not going to throw a lot of math at you, a little bit coming later on, but for the most part, let's think about this rather simply. If you have more solids and tougher solids, things like flushable wipes that historically weren't a problem, weren't an issue, things that were supposed to be tough and stringy and fibrous that people were supposed to scrub hard, and those things didn't go into the systems before they became a concept, before they really emerged in recent decades. So if you increase the solids level loading that you have going into your system and you decrease the water content, well then your balance or your proportion of difficult things or difficult proportions that we're going to deal with, it's just a matter of basic fractions. It's going to get worse. Your clogging situation is going to become harder. And so the ultimate result of all this is stories like the one posted just the other day from the city of London, where they had a fatberg that was the weight of a building that they had to remove from one of their sewers. It's pretty disgusting, right? And people see stories like fatbergs and they'll go take a look at those and click on them and they'll be fascinated for a minute. They might even hear the message briefly that, oh, we shouldn't put a lot of things into our wastewater systems. And they might learn that for a half second and then the story's gone. And then it gets neglected again. And we're back once again to the problem of solids being in our systems. So what are we supposed to do about it? Well, ultimately, there are basically three different methods of dealing with solids. You can screen them out, you can grind them, or you can pass them and get them downstream to where they can be dealt with by more sophisticated equipment than you can within the collection system. Now, how does this all work? Let's go through these one by one. First of all, let's talk about screening. This is getting stuff out before it gets to your pumps. Now, screening can do a really good job. It can keep many solids out of your system. And there are a lot of different varieties of ways that we can screen. We can approach this in different ways, manually or automatically. You can have highly sophisticated systems. You can have something that's as simple as a trash rack. But doing something to keep the solids from getting into the system in the first place, putting up that do not enter sign, that's a pretty good first step. That's a good way to start approaching the problem. The downside to it is that any kind of system, whether it's automatic or manual, is going to require some ongoing attention and maintenance. You can't just set it and forget it. If there are solids getting in and we have to capture the solids and remove them before they get pumped through the system, well then the thing that does the capturing is going to require attention and maintenance. It's going to require work. You're going to either have to pull the trash rack up and clear it. You're going to have to clear the dumpster that you've got sitting outside your automatic screens. You're going to have to do something. You're going to have to collect it and take it someplace else. Regrettably, this is not a Ron Popeil machine. Setting it and forgetting it just won't work. It requires that ongoing attention and maintenance, which means an investment in labor, an investment in time, an investment in effort, as well as an investment in maintenance and upkeep. Because unless it is the very simplest manual trash rack, it's going to require somebody knowing how to fix it, how to make it work, how to keep that piece of equipment in good repair. And keeping equipment in good repair isn't the whole story. Of course, it also requires disposal at lots and lots of different places. You may have to use something like a rollaway, and it may come from somebody who's got the best named garbage service on planet Earth, I suppose. But no matter what it is, the disposal has to be done somewhere, and it has to be taken somewhere, and the solid disposal has to be performed. And if you have a big collection system with lots and lots of sites where the solids are being collected, that means lots and lots of sites where you're going to have to travel in order to collect the solids and get them away from the system, get them carried away. That's going to take time, and it's going to take effort, and it's going to take maintenance. All of these things require an ongoing bit of maintenance. Now, when we're also working with these solids collection systems, screening things out doesn't do the whole story, doesn't capture everything. Now, if you've got a bar rack, right, your bar screen that has a lot of tightly spaced teeth, well, this may do a really good job of capturing things like round solids. You'll catch that baseball or that Nerf football that's somehow gotten its way into the system. You'll collect the Barbie heads. You'll collect those large things, but you won't necessarily collect those stringy and fibrous solids. Once again, back to our problem with things like flushable wipes. A wipe can go right through here. If it doesn't go right through here, it may very well bind against here, meaning it has to get cleaned out. But it doesn't necessarily capture things that want to flow, that want to wiggle, that are soft or that are malleable. If they can wiggle their way through the system, you're very likely not going to be able to capture all of them before they make their way through, which means this isn't a silver bullet. Now, you can get a really good job done if you have something like a perforated plate screen, but of course, this introduces a couple of problems of its own. It also has to be cleaned routinely. If it captures a lot, it has to be cleaned a lot. It has to be maintained. A perforated plate screen also is going to introduce head losses potentially into your system. And if one of these gets cleared or gets so full that it gets bound up, it may block whatever you are, wherever you're collecting from, and cause backups upstream, which itself presents a whole different story, a whole different problem. So this requires a lot of attention, a lot of maintenance, a lot of cleaning. Those screens risk binding if they are not properly cleaned. So properly cleaning a screen may very well mean that you can effectively get a lot of solids out of your system. But your worst case scenario potentially means that your worst solids may end up getting deposited into the system at a time when you are potentially least able to get to them. For example, if you have a system that inadvertently, or because it's a combined sewer system, collects a lot of storm debris, well, that means that you're going to get a lot of debris coming in at the worst possible time because your flow rates are going to be high and you need the largest amount of throughput. But if those solids come in and you get things like leaves or you get other debris that binds against a screen, potentially that means somebody has to go out and clean it out. Somebody has to go out and clear it so that you can continue to get the flow going through. But the problem is that if those worst case scenarios occur at a time when you have something like a lot of storms going on, that's the time when it may be most difficult to get to your wastewater collection system, because where are pump stations located? They're located at the bottom of a hill, not at the top of a hill. Well, if it's muddy because it's been raining, and that rain is what's been putting all the solids into the system, that may be the worst possible time to expect somebody to be able to get to the site to clear the things out of the screens so that your system can keep working instead of backing up upstream. So it's a big holistic issue. You can't just look at one piece of this. You have to look at the whole story. And those screens risk binding if they are not properly cleaned. This requires, again, ongoing maintenance and attention. Automatic screens are going to have a lot of different things that have to be taken care of. Gears, motors, sprockets, wash water, your brushes, and of course, again, your cleaning and disposal. Even if you have a purely manual system, you're still going to have to go out and clean it and dispose of the solids that are collected on a regular basis. I will not tell on anybody, but I've seen far too many systems that have a rack that's available, a manual kind of trash rack available to capture solids before they get into the system, where that trash rack has not found its way back over the influent pipe. Somebody cleared it and then just didn't put it back because it got to be too much of a hassle. Well, we understand that it seems like a hassle, but the fact of the matter is if it's not capturing those solids before they get in, they're going to go through that system and they're going to get deposited someplace else. So, method number 2 of dealing with these solids is grinding. Taking big things and turning them into little things. Now, sometimes it's a necessity to take a big thing and to turn it into a little thing. I'll give you an example here of a story from a guy who likes to do things just a little bit differently from, I don't know, what any normal human being would expect to do. It's a guy who runs a blender company, and they do this little series, this video series they call Will It Blend? It is ridiculous and silly, but I think you'll enjoy it.
Will it blend? That is the question.
He's built an entire empire off of this, so I'm pretty impressed by the fact they can pull it through. But we're going to talk a little bit about the unreality of this system.
iPhone 11 has been great, but now it's time to get the latest. Now, I understand that the iPhone 12 was not announced at this year's Apple event, but my inside sources lined me up with the latest iPhone, the new iPhone 12 Pro Max Plus Plus. That has a really cool app, and all I have to do is dial 10 numbers and I can call anybody in the world. The real question is, will it blend? I think I'll press the new brick button. Sounds like old technology. Don't breathe this. It doesn't look like the new iPhone is very advanced, but we'll blame it on 2020.
Okay, the ridiculousness of this story aside, check out just something here as we're thinking about blending something as stupid as a giant phone. When he's putting this system into a blender, what do you think he's got going on with the blender teeth here? That stuff is hardened, right? And it's not just rotating at an ordinary pump rotating speed of like 1200 or even 1800 RPM. This thing is moving fast, okay? It's designed to do that so that it can take care of solids. But all that work that it had to go through to chop up the old brick phone is a good example of what it takes in order to take a big solid and turn it into a smaller solid. There's a lot of effort that's required. You have to have resilient parts. You have to be turning things at a really high speed. And you have to expect that there's going to be a lot of damage potentially done further downstream into your mechanism to make this whole thing work. You have to give up something in order to get to a point where you can have a system with a high amount of throughput dealing with solids. Now, you may have no choice when it comes to things like small diameter sewers. You may very well have to grind up everything at the source before discharging it out anywhere else. If you're that close to the lakefront, it may be the only thing you can do. So in some certain cases, there's no other choice but to grind things up before pumping them along. But it potentially is bad for pumps to also try to grind. I like to tell people that, when you think about a vehicle, for instance, the old El Camino, is it a car? Is it a truck? Is it a little of both? Is it a great thing at doing either one? Maybe or maybe not. The problem that potentially you have when you have something like a pump that's trying to also grind is when it's trying to put that force through and that rotative motion that's going through the shaft and going through that pump into the impeller and into wherever it's dealing with the solids, every time you encounter a solid with a rotating piece of equipment, there's going to be shaft flexion, right? It's going to move things around. This is why over a pretty short period of time, you should generally expect that grinder pumps are going to encounter some kind of difficulty with their bearings or their seals, because there's just perpetually going to be shaft flexion, right? Things are going to move back and forth as they're trying to rotate through and grind up and encounter those solids. That potentially leads to, I won't say premature failure, but earlier failure than you will have for a system that's not trying to grind up those very same solids. Grinding can also, though, contribute to clogging. What happens when those fatbergs that we have out there collide with ground solids? Just this shot looking down into a wet well, you can see all of this floating FOG on top of that wet well surface. There's all kinds of stuff here that wants to bind, right? It wants to collect. It wants to touch something else and stick to it. Well, what happens when those ground up solids encounter this kind of stuff? It makes things stick together, and it potentially makes those problems bigger. These may not be big for now. These may be chunks that are 6 inches or 12 inches for the time being, but they may turn out to be much bigger problems as they collect and bind against other stuff, particularly if there's a lot of surface area. Think about this. Think about a baseball going through a system. Now, typically we use 3-inch diameter spherical solids as sort of that baseline for what a solids handling pump is supposed to be able to push through. 3 inches in diameter is roughly the diameter of a baseball. Now, baseball should be able to pass through a system intact if you've got adequate clearances involved. If you don't, or if you chop it up, if you macerate it, if you cut it up into pieces, the component parts of a baseball potentially are far worse than trying to deal with a baseball that's entirely intact. Because if you think about it, inside you may have your cork, your rubber, or something that's holding the ball together, depending on what quality of ball you're dealing with. But you also have a bunch of string. And that string is the real kicker here. Because string likes to catch on stuff. String likes to collect into bigger pieces. Again, it's a stringy, fibrous solid. This is the problem that we have with wipes, and it's the problem that we have with other solids as well. Stringy stuff you much would rather have captured inside the body of the leather baseball rather than getting exposed and caught out in the open surface where it can get captured and collected along with those fats, oils, and greases and lots of other things. Stuff that gets sticky gets harder to pump along. And that makes for bigger problems potentially. Additionally, dealing with any kind of a grinder system, whether you're talking about a grinder type pump or whether you're talking about a full service dedicated grinder that's in line with your system before it makes its way to the pumps, is going to require maintenance. You're going to have to do some kind of maintenance, say on the grinder teeth. You're going to have to replace those from time to time because you're going to occasionally have irreducible solids. rocks and metals, things that are too heavy to flow through. They're going to fall down. They're going to have to get captured. You're going to have to remove those from your system, potentially before they do damage or after they've done their damage to your equipment. That's why you're going to see things like on the bottom of an inline grinder, you're going to have a plate you can remove to remove those solids that have gotten deposited and stuck and lodged down below. And just as when we're dealing with screening things out of a system, you can think of a grinder oftentimes as acting as a sort of a pre-screening mechanism. But if this gets clogged up and this doesn't get cleared out, then you're going to bind up your system. You're going to reduce the flow through that you can have going through because you've taken the effective diameter of your pipe and you've reduced it. Now you have to get this cleaned out so that you can potentially get the full flow going through the pipe that you expect. This is another maintenance issue. Doesn't mean it's insurmountable. Doesn't mean that sometimes this won't be required, but it has to be considered. This is not a set it and forget it issue. You have to do something to deal with those solids that are going to try to go through that are otherwise irreducible. And anybody who says that a system is going to be completely impervious to clogging hasn't seen the kinds of stupid things that some people will put into their wastewater systems. They just will. Which brings us to potential item number 3. Strategy number 3 for dealing with solids, and that's simply passing them through the pump, making sure that they go right on through. This is why we want to have large open veins inside things like our impellers. We want a large, wide open space for solids to go through. Now, the thing about this is wide open veins, great for solid passage, terrible for hydraulic efficiency. That's because centrifugal pumps, which is what we're mostly talking about in wastewater systems, need to be able to produce their force, be able to take that energy from rotation and convert it into pressure and flow from a pump and the flow that's going through with the fluids. They do that by rotation, and they do that by exposure to the veins. The veins are what usually cause that energy to get transmitted into the system and into the fluid. Well, more veins would mean more efficiency. Fewer veins means more solids passage can go through. Now, you might be able to escape this by doing something like a vortex passage where you recess the impeller away from the flow and let that vortex create the pressure itself and escape it that way. But it's not entirely possible to do all the time. It's potentially something you can approach, but you still have to consider the ability of that flow to pass through and the solids to pass through as well. Now, you can address this as well with things like single vein impellers and some certain strategies so that you can get a large passage area and keep things from clogging. There are lots of different strategies that we can use to approach the solids that are going through. But no matter what, when we're dealing with a pump, we have to think about what way we're going to address the solids. Are we going to have wide open veins? Are we going to have vortex passage? Are we going to have a single vein potentially to move things through? We have to think about this because anyone who tells you that a pump is non-clogging is using a marketing trick. They're using a catchphrase that really doesn't mean anything. Because I can tell you from my own personal experience, having seen people do things like flushing beach towels into wastewater systems, that there's no such thing as completely non-clog, right? There's going to be a bad worst case scenario that's going to come along at some point or another. When I get a call and I get told that a pump is clogged and a pump has trouble, we have to find out what the ultimate source of the problem is. There have been times when I've encountered things like 2x4s clogging into a system. I can't control the passage of a 2x4, nor can you. You simply have to be able to address it, figure out how it got in, and then figure out how you're going to get it out. Now, why would you want to pass a solid? You're not going to hope to pass a 2x4. You're going to have to just address the 2x4. But in a lot of other cases, we may want to put things through, like putting it through a tunnel, because it's better to let that solid go through and get to a place, get to a destination, say at the headworks of a wastewater plant, where we can deal with it effectively, rather than just crossing our fingers and hoping for the best. Now, the real answer to keeping things that are large while they go through a system is surface area. I want you to think about cleaning your dishes, right? When you clean your dishes and you've got something that's a really big mess, you're going to use something like a sponge. Why do I use a sponge when I'm cleaning things? I do that because sponges have lots of surface area. There's lots and lots of area here to grip the solids, to wipe those things off, to collect the soap, and to help increase the amount of surface area that's working with every wipe that's working on top of those dishes. The larger the surface area, the more work that gets done. The more cleaning in this case when we're dealing with a sponge. But there's a flip side to this, because not every time do we want large amounts of surface area. Think about that 3-inch diameter solid that we were talking about. Pushing that 3-inch diameter solid through the system is, let's just visualize it here as this 3-inch diameter ball. That has a volume, if you go back to do your old math courses, 4/3 pi r cubed. That's the volume of that sphere. I'm not going to make you do all the math on this, but let's just say we're going to take that diameter, that volume of a 3-inch diameter sphere is going to be about 14 cubic inches, just a hair over that. That's the amount of total space inside that sphere. Now, take that same sphere and divide it up into 4 little pieces. Chop it up, and I'm just using 4 because it's just an easy number off the top of the head. Take and divide it into those 4 pieces. That same volume here, just slightly over 14 cubic inches, that diameter, each one of those is 1.89 inches in diameter. Okay, that's assuming this has been evenly split and they all form back into spheres. We're just going to use that as a simple scenario because it's apples to apples comparison. Same volume, but the diameter is smaller. Okay, 4 just slightly less than 2-inch spheres, about the same volume as that single 3-inch diameter sphere. Now that's how it looks like when you chop that solid into those 4 equal pieces. But the thing about it is that when you've chopped it up and you have the same total volume, right? The solid itself hasn't disappeared. It's just been chopped up into those 4 equal-sized pieces. The thing that's not equal about it is the surface area. That single 3-inch diameter solid has 28.27 square inches of surface area. It covers the same volume, but that's the outside space around that sphere. Just over 28 square inches. That one single 1.89 inch diameter solid has 11.22 square inches of surface area. So each one of these has just a hair over 11 square inches of surface area, which means that when you have 4 of them, because you have to have 4 of them to equal the same volume as this guy, you actually have a total of 44.88, or just shy of 45 square inches of surface area. So 28.27 versus 44.88. Again, I won't make you do the math. What we've done here is, instead of having this single solid with this amount of square surface area, we've increased the amount of surface area by 59%. We've taken that big problem, that big 3-inch diameter sphere, and actually turned it into a bigger problem by making the solid smaller. Because when there's 59% more surface area for every single solid that's gone through, that's 59% more surface area to encounter stuff that wants to stick together and wants to make our problem bigger. That's why pushing solids through a wastewater system at their full scale, at their full size, without reducing them down, actually may be a much better way of handling those solids with much less work, far fewer headaches in the system than by reducing them down. You don't have to do all the math to just see making a big problem smaller may actually make that small problem much bigger. And making that bigger potentially means much greater headaches down the road. Now, most of the time when people are looking at things like this, they're just some very simple boxes that people like to check when they're designing a system. They're checking off, okay, well, do we have a certain amount of solids clearance, or do we have a way of handling the solids? Yep, check that box and move right along. But I'm going to caution you that that is not the full picture. That's not the whole story, because all too often then the question is asked, well, what's the efficiency of the pump? You can give any pump a rating for its hydraulic efficiency. You can take a look and see just how much energy that's gone into the pump is transmitted into pressure and flow going out. And that's its hydraulic efficiency. But that doesn't tell you the entire story about what the efficiency really looks like. Now, does efficiency matter? Sure it does. Absolutely. Anytime you're putting energy into a system, finding out what you're getting out of that energy is worth asking. That's an important set of questions to look at. So efficiency certainly matters. Not everything's going to be as neatly streamlined as a train looked like back in the 40s or something like that. But we do want to make sure that the energy that goes into the system goes into actually doing work, right? We want it to produce good work. But we want to make sure that we're looking at the whole picture here. We're not just looking at an isolated segment or section of the total picture of efficiency, because there are lots of different types of efficiency. This wind vane, this collection of energy from the wind and turning it into electricity may be a very efficient way of approaching things and for delivering electricity to your house. But what happens when this system breaks down? There has to be a backup, right? So when we're collecting renewable energy, there has to be something to balance out the load. Either we're collecting it and storing it in large batteries, or the counterbalance to a wind turbine is that you have to have usually a natural gas power plant running side by side with it so that you can balance the load, because demand goes up and down, but it doesn't go up and down at the same rates as the wind blows or doesn't blow. It may be highly efficient, but that's not the whole picture, right? There has to be something else to make sure that this whole system for electricity works. Well, hydraulics are the same way, and wastewater collection systems are the same way. The energy that's being collected or being used is just one piece of the whole puzzle. It doesn't tell the whole story. That top line energy efficiency is really easy to measure. Anybody can look at a pump curve and see what the hydraulic efficiency number is. And it's easy to say, well, this pump says it is 68% efficient at this condition point, so the pump that we want must be at least 68% efficient, and that becomes their specification. Top line energy efficiency, really easy to do, right? But just because it's easy doesn't mean that it's the correct story. As we often hear from people talking about things like management, what it matters must be measured, or what's measured is what then is believed to matter. Well, just because we can measure it doesn't mean that it's the whole picture. And just because we have a harder time measuring other things doesn't mean that they don't matter, because they really do. Easy to measure isn't always the most important thing. If you go to the state fair and you see the giant hog, well, sure, it's the biggest. But is the bacon any good? I mean, the question isn't the whole picture. The single top line number, the easiest thing to measure, how fat is this hog, isn't the whole story. It doesn't tell us everything that we need to know, and it doesn't tell us everything that gives us actionable information about what we need to do about our system to make it work right. And I want people to think systemically, because every wastewater system is in fact a system. Just because something has broken down in one part doesn't mean that tells you that the whole system is broken down. Or just because you've identified something that appears not to be working doesn't mean you've fixed the systemic problem that you're dealing with. All too often, I'll get a call from somebody who says, well, the pump's broken. Is the pump broken, or is the system broken? Maybe it's the system. In fact, in my experience, the majority of the time, it's not actually the piece of equipment that you're looking at that appears to be wrong. It's actually the system that has the problem. So let's think systemically. Let's think about the whole picture. I say hydraulic efficiency is overrated. Now, I want to qualify that. When we're talking about wastewater efficiencies, it's overrated. Doesn't mean that it's not important. Does mean it's not the whole picture. It's not the entire story. And we need to think about the entire story to make the right decisions about what we're putting into our systems. More vanes would mean more hydraulic efficiency. Going back to that picture I showed you earlier, where we had a 2-vane impeller and we had a baseball inside that could fit through the entire place. If we added 2 more vanes, which I did here just by taking the picture and rotating it 90 degrees, I could add more vanes. This would make this impeller more hydraulically efficient, right? Because more vanes would do more work with every turn of the impeller, and so we'd have a much more efficient, hydraulically, a more efficient pump. But the fact of the matter is, if I added more vanes, there would be no place for that baseball to go. We could no longer pass a full 3-inch diameter spherical solid through this particular vane, which started out as the same thing. I just copied it and rotated it 90 degrees. That would be much more hydraulically efficient, but it would not be solids efficient. Well, what do we call that? That's operational efficiency. Operational efficiency is achieving what we try to do. What we're trying to do here is move wastewater that may contain solids and move all of it effectively, not just the water part. Because if this impeller gets clogged with that baseball, it's going to cease to be a particularly useful pump impeller to us. If this thing is just banging around there eternally, this is going to steal all of that neato hydraulic efficiency that was easily rated and easily measured and easily charted by adding additional vanes to the impeller. But that doesn't make it an efficient pump. I mean, you could look at one of the most efficient pumps that's out there, a horizontal split case type pump. These things are incredibly hydraulically efficient. It's not uncommon to see these things in the 80s and sometimes even the 90s for percentages of hydraulic efficiencies. They're phenomenal for moving water with using the energy as efficiently as humanly possible. But these things would be wildly inappropriate for pumping sewage. You'd never try to put solids through this impeller. That would be stupid. That would be a terrible idea. That's because this is hydraulically efficient, but it's not operationally efficient if we're dealing with something that may contain solids. And the problem is, the worse the solids loading, the more important it becomes to consider operational efficiency and not strictly the hydraulic efficiency. The The hydraulic number alone matters, but it isn't the whole picture, and it can't be used as the cutoff to tell us what works or what doesn't work. For that, we have to look to the whole picture. The operational side tells us what it is that we're doing with our time, with our energy, with our money, with our maintenance costs, with all the attention that has to get paid to keep that system working. Getting to that level of operational efficiency is vastly more important than strictly getting a good hydraulic efficiency number out of our pumps. Think about hydraulic efficiency as a part of a whole picture. Energy consumption matters. Of course it does. Paying the power bill matters. Making sure that you have backup power for a system matters. And the costs of all that matter. But also, things like clog resistance matters. Keeping the clog from getting into the system and to cause a problem, that matters. Keeping the pump from clogging when something does get through, because perhaps it wasn't caught by screens upstream, or because the grinder system that we put in actually made the clog worse potentially by, as we've talked about before, increasing the surface area and making it more possible for things to capture and get stuck together. So the speed to unclog the pump is incredibly important. Now, this doesn't rate very well in terms of hydraulic numbers. It doesn't show up on a pump curve. It's not going to show up as we're looking at that question of, well, what does the efficiency number say? But the speed to take a clog out and get a pump back into service, that matters a huge amount when it comes to operational efficiency. And so does the frequency of breakdown. How often do you have a problem that keeps a pump from working that then has to take time, effort, sometimes equipment, sometimes repair parts to get that back up and into service? The frequency of a breakdown has a huge impact on the operational efficiency, but it doesn't show up on a pump curve. That doesn't mean it doesn't matter. It matters, and it matters enormously. The longevity of the wearing parts matters a huge amount. When given the choice, anytime I'm given the option to recommend parts to people, I'm going to say, particularly in sewage applications, get the longest lived parts that you can. The ones that are going to have the longest service life, put them in now, put them in when you can pay for them out of your capital expenditure budget, rather than having them suck money out of your operational budget later on. You want things that are going to last the longest possible time so that it requires the least amount of intervention, the least amount of effort. You do want to achieve as much as you can of that set it and forget it by being able to get there by getting the stuff that's going to last the longest once it's installed. And it also matters how quickly can you recover once there is downtime. Every pump station that's dealing with solids from time to time is going to have downtime. Sometimes it's because of random things like turtles making their way into a collection system or muskrats. Sometimes it's because other things have gotten into a system that then have to get removed. You stay in this business long enough, you're going to see the weirdest things get in. The question is, how do we get them out? Did we pre-screen them? Did we grind them down if that was the appropriate way to approach them? Or do we have a way to get them out of the system and get the pump back into service? Because downtime matters. Again, it takes time and effort. It may also require bypass pumping. It may require a lot of other things that are investments, things that are going to cost money, things that are going to take resources away from other work that can and will need to be done. That's why overall, what we call life cycle efficiency is what matters the most. The old story about Gillette was that you could give away the razor and sell the blades. Same thing goes if you get something like a Keurig, right? Love to have those things because they're very quick and efficient for making a single cup of coffee at a time. They can more or less give away those machines because they're going to make the money off of selling you those K-cups, those pods, every time you want to get another cup of coffee. That costs more than just getting a big old canister of folders and making it in the conventional coffee pot. So you have to look at the whole picture. The K-cup may be a really efficient way of making one pot of coffee at a time, but it will cost more on an operational side because you're going to have to pay more to get the exclusive little piece of equipment here to make the whole thing work. The whole picture, the whole holistic life cycle cost of what you're getting is what matters. And that's what you have to look at, not just a strict question of hydraulic efficiency. Now, I was talking about unclogging because it's really important when we're dealing with pumps, because stuff gets in. I just cannot reinforce that or overstate that too many times. Stuff gets into systems and we have to be able to get it out. Can you get directly to the clog? If you have a pumping system that's in place, can you approach it, get to it, and pull it out, get the pump back into service quickly? I have a predisposition, a bias, and I'm going to admit it up front. I like pumps that are above ground because that's where people are. If nobody has to go into a hole or stand over a hole and winch something out and remove the pump to get to the clog, hey, if I can avoid that just by being at ground level to deal with it, that's my preference. I'm thinking that's going to work a lot more efficiently, and it's going to be a more pleasant environment. Nothing's great about working with wastewater, but the more pleasant you can make it, or at least the less unpleasant you can make it, the better off you're going to be. And being able to immediately remove a cover plate and access the solid that's going to get caught in the impeller, remove it immediately and put it back into service, this, to me, is the preferable way to go. The easier you make it to get to the clog and remove it, the faster you can return the pump to service, and the faster you can get back to operations. That's operational efficiency. Can you resume service quickly? That's what really matters here. Anybody who's been stuck in an airport, seeing a bunch of cancellations go by, knows what it's like when a system shuts down and you can't get to where you want to be. Well, wastewater collection systems are the very same way. We're trying to get the water to where it needs to be so it can get treated. And if we've got cancellations, if we've got shutdowns, this matters a whole lot more than a top-line hydraulic efficiency. What can the pump do to protect itself? This matters a lot, okay? No matter which of the different strategies you're using to deal with solids, whether you're trying to screen them out, whether you're grinding them out, or whether you're trying to pass them, the pump has to be able to defend itself. And probably, hopefully, defend itself a little better than the cops can when they're driving this little clown car. We hope. But you've got to be able to defend yourself somehow. A couple of different ways that this can be done. And I'm going to show you at least a newer technology that Gorman-Rupp is offering that's one way to approach this. They took their conventional solids handling wastewater pump. They said, all right, well, if we've got things like wipes going through, how do we cut those things up? How do we approach that? They did that by introducing a combination of just two pretty simple items. Taking the wear plate that the impeller rotates against and serrating it so that there are little places here that effectively help to slice things that get caught going through. And the other thing that they did was introduce this little tooth that pokes in from that wear plate to disrupt the flow right near the eye of the impeller. Now you look at that and you say, that potentially could reduce the hydraulic efficiency because we're disrupting the flow as we go to the eye of the impeller. Well, disruptions should potentially make it somewhat less efficient, wouldn't they? You're absolutely right, they do. But there's a trade-off here. The trade-off is that flow disruption keeps things from getting hung up. This little illustration will sort of show you what it looks like as it's going through. Now, the system is designed for dealing with solids. It's designed for dealing with really bad solids. Initially, they said, well, let's try this on dealing with things like chicken feathers, things like poultry plants. Then they thought, well, it turns out that those chicken feathers are a whole lot like dealing with fibrous, stringy wipes and things like that. So this is where we've taken that impeller, or taken that cover plate off, the wear plate that's sitting there against the rotating impeller. That is where all the action happens. The stringy solids get pressurized as they're discharged out through the pump. That's the idea. But as they get caught sometimes, that's where you have those wipes and other things that want to get caught on the leading edge of the impeller vane. You might want to disrupt that flow. And that's what that little tooth is designed to do. It's disrupting the flow so that it gets dislodged from the impeller and gets pushed on through the pump. Sacrificing hydraulic efficiency in order to get higher operational efficiency, because we don't want the wipes that want to get caught on the leading edge of the impeller vane to cause a clog, to get caught against the FOG or other things, binding and creating a bigger solids issue. We want them to move through. We want to pass them through so that the pump can remain in operation. That's being operationally efficient, even though it sacrifices a small amount of operational efficiency. I'm not saying that this can't be a little bit fun as well. When this was introduced at WEFTEC, you'll see here an employee who's got a demonstration model. This pump is in operation, and that's a rubber chicken. He's going to shove it into the system and get it shoved into the pump, sucked through, and discharged out. Sometimes dealing with solids can be fun when the water is clean and it's a rubber chicken that we're dealing with. But when they're much worse solids or much more difficult solids that we've got going through, you want those things to pass through sight unseen without you noticing them. That's the idea that we're after. So technologies can help us do this. This is one example of one manufacturer's technology. Other manufacturers offer other technologies for dealing with these solids. But overall, the question is, what is operationally efficient, not just hydraulically efficient? Because downtime costs money. It means costs to bypass. It means other expenses that are involved. Downtime means the potential for solids to get settled in the force mains. As those solids settle in, those things then are harder to dislodge going down the road. You want flow at all times, and you want flow at good velocities, 2 feet per second or better. You want to move things along and carry them to where they can be dealt with, usually, again, at a headworks facility. And downtime means other things don't get done. This is the real problem that oftentimes doesn't get discussed. The more municipal budgets are stretched, the more public works departments are expected to do more and more. The more people who are working in one department get brought over to work in another to keep things balanced and to do all the work that we can. And the more those budgets get compressed and tightened because people don't want to pay taxes and because budgets get stretched and cut all the time and nobody off the top of their head goes, hey, you know what we need is a 50% larger wastewater department budget. Because we don't have a lot of that, downtime means other things don't get done. So we want to reduce those things at the source, address them at the beginning, and keep them from becoming a problem. Prevention remains the best cure. Educate your community. Remind them a toilet is not a trash can. Push back against this idea that wipes are flushable. They are not. Don't use the language yourself. Don't let anybody you know get away with using that language. Maintain your force mains and your collection systems. Maintain them well so that things pass through. And if that means you got to jet them once in a while, jet them once in a while to keep things flowing. Use those trash baskets and those other screening tools that you have to keep things from getting clogged. And insist on equipment and facilities that you can safely maintain. If you can keep them up normally with good conditions, that's going to lead to higher operational efficiency. This is all about preventing clogs. But from time to time, clogs are going to happen. From time to time, solids are going to get in that we can't screen, grind, or pass through, and we're going to have to deal with them. So act like a doctor. First of all, do no harm. Don't make big problems even bigger, even if you think you're making them smaller. Cutting things down to size does not mean you are making your problem smaller. It may mean you're actually making your problem bigger if you're adding more surface area. Don't confuse hydraulic efficiency for operational efficiency. Just because a number shows up on a chart doesn't mean that's the solution to your problems. And don't make it hard to solve your own problems in the field. We don't want downtime. We want systems that are reliable, that are dependable, that are going to keep on working and moving things down the line to where they can be dealt with. That's what really matters here. Not just the amount of energy that the pump is using that can be measured. What about your energy, your time, your maintenance efforts, your expenses? All of those things matter. Keeping a system working operationally efficiently is more important than doing it strictly from a hydraulic standpoint. So, to recap, solids problems do seem to be getting worse. Yeah, they are. Blame wipes, among other things. This is making life harder. So, screen them, grind them, pass them, think through the full range of options and consider all of them. Sometimes more than one may be necessary to do the job right. Don't cut corners, though, where critical downtime is involved. Do not sacrifice operational efficiency just to get another notch or two for hydraulic efficiency, because operational efficiency is what is essential, especially when we're dealing with wastewater. So please, think of yourself about acting like a doctor. Treat the whole patient, treat the whole system, address everything that you're working with your system to make sure that it works right. If you have any questions, please feel free to call me anytime, shoot me an email. I'm happy to help. This is a difficult job, everybody knows it, but the more we can do to make your life more operationally efficient and just more livable, the better off we're all going to be. I appreciate your time.